Model Parallelism LLM and RAGProjects. Definition. The technique of splitting a large language model LLM or retrieval augmented generation RAG model across multiple devices to parallelize computations and handle larger models than a single devices. Memory capacity. Key components. Large language models LLM. Models like GPT-3, BERT, and other transformer-based models that require significant computational resources. Retrieval augmented generation RAG. Combining information retrieval techniques with generative models to enhance the accuracy and relevance of generated text. Parallel computing. Distributing computations across multiple processes or devices to improve performance and scalability. Inter-device communication. Mechanisms for data exchange between devices, such as GPUs, to synchronize computations. Methods. Tensor parallelism. Splitting the model's tensors weights and activations across multiple devices. Pipeline parallelism. Dividing the model into stages, where each stage is handled by a different device, enabling simultaneous processing of different parts of the input. Data parallelism. Replicating the entire model on each device and splitting the data across these replicas for parallel processing. Hybrid parallelism. Combining tensor, pipeline, and data parallelism to optimize resource utilization and performance. Tools and technologies. PTorch distributed. A PTorch module for distributed training, supporting various parallelism strategies. DeepSpeed. A deep learning optimization library that simplifies distributed training and model parallelism. Horovod. An open source framework for distributed deep learning, supporting TensorFlow, Keras, PTorch, and Apache MXNet. Megatron LM. A framework for training large transformer models with model parallelism. Developed by NVIDIA. Ray. A distributed computing framework that supports parallel processing for machine learning tasks. Applications in LLM and RAG. Large-scale training. Training very large language models that exceed the memory capacity of a single device. Efficient inference. Deploying large models in production environments with reduced latency by parallelizing inference. Computations. Enhanced generation. Improving the relevance and coherence of generated text in RAG systems by leveraging larger models. Scalability. Enabling scalable training and inference solutions for enterprise-level AI applications. Challenges. Complexity of implementation. Designing and implementing parallelism strategies can be complex and requires expertise. Inter-device communication overhead. Ensuring efficient data exchange between devices to minimize communication bottlenecks. Load balancing. Distributing the workload evenly across devices to prevent underutilization or overloading. Debugging and profiling. Identifying and resolving performance issues in distributed environments can be challenging. Resource management. Optimizing the allocation of computational resources to maximize efficiency and minimize costs.